nuevamente, Roberto. Aquí me arranco. Primero, bueno, I guess, will you speak in English or? Yep. So I'll introduce in English, just in case. Welcome everyone to the Seminario of Applied Math, organized by the Institute of Mathematical Computational Engineering. So today we have the pleasure of having our own Roberto Cominetti, our very own Roberto, who is a professor titular, full professor here in La Católica. He obtained his degree in mathematical engineering at the University of Chile in 1996. He then went on to get his PhD in France in the Université Blaise Pascal in 1989. And then after that, he had a very fruitful career here in Chile as a professor, first as a professor in the University of Chile, then as a professor in Universidad de Valles, and then, thankfully, now here in Universidad Católica. His main research, show us today, but it's in optimization, in convex optimization, algorithmic game theory, fixed point iterations, microprocesses, and equilibrium dynamics. So let's give him an applause for that.
Okay, thanks for the introduction for attending the seminar. So my plan for today is to sort of provide a summary of several related topics that we have been working for a long time now. It's about 10 years. With a bunch of colleagues, mainly in Chile. So they will appear, as we go on. But Mario Bravo, Jose Weissman, Jose Soto, also Jean-Bernard Cagnon from France. So there are inputs from many sources, and the topic is about fixed point operations. We got interested into this because of a very nice paper by Bagnon and Brook, the 90s, which is amazing, this paper, because there were almost no results, but several conjectures, about 10 conjectures. And then later on, they solved some of these conjectures, others remain open, and we got interested in, and then it was very fruitful. And so I'm going to tell you a little bit of the story of this. And the framework is very simple. You're given a Norman space, general, and it's not much structure. It could be any Norman space. And you have an operator, T, which is non-expansive. It might or it might not have fixed points, so we will assume from the start that it has a fixed point. And the goal is to find algorithms or iterative procedures that allow you to get an approximate fixed point. Like this, I mean a point in the space such that the fixed point radiator is small, smaller than epsilon. So as a warm-up, we all know about contractions. This is very classical, the impact of contractions in mathematics is really everywhere. It all goes back to, you can backtrack that to Liouville, P30. So it's a very long classical subject, but the standard way to present this, the topic is due to Banach, or Banach-Picard if you're French, or Banach-Picard-Cacciopoli if you're Italian. So there are many names for this result. The result says simply that if you have a map which is a strict contraction and the space is complete, then not only it has a unique fixed point, but it's very simple iteration, which is Banach-Picard. You just iterate the map, and it will not only converge to a unique point, to the unique fixed point, but you also have explicit error bounds. And this is our main interest. What type of explicit error bounds can you get out? In the case where rho is equal to 1. So if you look at this, and this is very simple to obtain. So the difference between xn and the next iterate, because of the contraction, you have this control. in terms of the initial residual. So it's very explicit. If you give me an epsilon, I can predict what n should I take, how many iterations should I do to get an epsilon solution. And not only that, from this you can also, once you have found the residual, you can also estimate the distance to the fixed point. The distance from xn to the unique fixed point is just a factor 1 over 1 minus rho the residual. That's almost perfect, but we can expect as a result. But if you look at this and you assume that your contraction coefficient is 1 or even close to 1, this is not totally satisfactory. In fact, if rho is equal to 1, this second inequality only tells you that the residual will not become bigger. That's all. And it doesn't assure you that it goes to 0. And the first is estimate, of course, it's millions, 1 over 0. So the question is, what happens when rho is equal to 1? And this has a very long story. So here is a very fast review of what has been done. Probably the first attempt was by Krasnodębski. He was trying just to prove that an operator, which is just non-expansive, does it have a fixed point or not. To do that, he came up with an algorithm. He proposed an algorithm, which is this one. Start from any x0, and then instead of taking just the image of your operator on the previous point, you average the previous point with its image, with some coefficient alpha n. In fact, Krasnodębski proposed to take alpha n equal 1/2. Just the average of xn, the current xn, and its image. That's it. You iterate that, and using that, he was able to prove some theorems about the existence of fixed points. He was not much interested in algorithmic aspects, but he used the algorithm just as a device to prove the existence of fixed points. Much later, that was in the 50s. Much later, not much later, in the 60s, Halpern proposed something which at first sight seems absolutely ridiculous. So instead of taking the average with the previous point, you take the image of the previous point and you average with the initial point. So you completely forget about the address. You already have at xn minus 1, you forget. You just go back to x0. So x0 operates as an anchoring. You always try to go back to 0. And although they look quite similar, they have very different practical behavior, and they operate on different principles. So I will try to come up with it later. Well, and later on, there is a host of different algorithms. Just don't pay attention to this, but just get the idea that there are many algorithms that in some way or another, they mix the iterates and the images of the iterates to build a new point and keep going. Those are where these iterations appear, where in many places. They appear, of course, as I said before, as an algorithm to complete fixed point, or as a method for proving the existence of a fixed point. That's one. But it also appears frequently in convex optimization. There are many algorithms which fall one way or another in one of these, mostly Krasnodębski map. So gradient descent, proximal point method, Douglas rats for ATMM, projection to convex sets, and so on and so forth. There are many algorithms that they all, by suitable defined with the operator T, they fall into this type of fixed point iteration. You have a question?
Yeah. Why is there this obsession with the rho equals 1 case? I mean, are there like?
I'm coming to that.
Okay.
I provide 6 examples.
Okay, good.
I provide at least 6 examples, but already here, all of these methods in optimization, they have to deal with a non-expansive map. Proximal point, the projection, if you want. The projection to a convex set is non-expansive. You cannot expect to have a contraction. That's already one example, but I'll come back to that question.
Yeah, so in the list of algorithms, it seems that you always look at the iterate and you look back 1 or 2 before that.
Yes.
Is this particular case of a general theory?
Yeah.
Okay.
I'll come back to the next slide. So already you have these 2 first things, but in stochastic dynamics, you get those very similar iterations, either in Markov chains or Q-learning, which is my favorite application, which I hope to arrive to provide a glimpse what are the issues there. Lazy random walks, legend dynamics. There are many dynamics which are not considered as an algorithm. Well, Q-learning, yes, it's an algorithm, but lazy random walks is just a description of a dynamical system which evolves stochastically. And you want to study the convergence of towards invariant measures. So you're not looking for an algorithm, but you have a model and you want to say something about this model. Does it converge? And so on and so forth. So in that case, the model comes already in the form of one of these iterations. And you can also look at this as a discretization of a differential equation. So all the theory on non-expansive semigroup of contractions, heat equation, and there's a full brand of works in that area which deal with this equation, and they use discretizations to prove, for instance, the existence of a solution of the differential equations. Okay, that's a big overview, and here come to your question. If you look at all of these iterations, well, in fact, they all go back 1 step, 2 steps, 3 steps. Well, there was in the 50s, in 52, almost simultaneously, but independently of Krasnodębski, there was this guy, Mann, German guy, who proposed this type of iterations. You will build a new pointing set by just making a convex combination of the previous images. So you look at the orbits that we have looked so far, and you average that. Okay? And these coefficients pi I n, they look like this. It's a triangular array of coefficients. They sum up to 1, they're not. You just do convex combinations of all you have seen up to now, or up to the previous iteration. So you see here, I have shifted x to I minus 1 from I equals 0 to n. There is a caveat here is that for I equals 0, there is t of x minus 1, which doesn't make sense. Well, this is just the initial point. So that's the convention, just to, okay, just to write it in that. So those are the general Mann iteration. These are sequential averaging procedures. And for instance, if you look at Krasnodębski-Mann, well, the pi n are built recursively, but you can backtrack and express the pi n explicitly by this expression. It's not very important. Well, just keep in mind that there are products of 1 minus alpha k. They will show up later. For Harper, it's simpler. Harper, you only put a weight on the initial point. So you have here, in this column, you have something, which is 1 minus beta n. All the rest is 0, and only at the diagonal here, you have the beta n. It's much simpler in terms of structures. But again, our goal would be to analyze this. But before we jump into the analysis, let me give you examples. And why do we care about non-expansive? Oh, before that, what are the questions? There are 2 types of questions. The first one, I give you the pi n. So the pi n is given by a model, or because I'm just interested in one specific algorithm, which Krasnodębski or inertial Harper. And I want to say something about that. What are the natural questions? The first one is the residual going to 0? Does it converge to 0? First requirement, needed requirement, right? Next, this is called asymptotic regularity, by the way. The jargon in this area is called asymptotic regularity. Next question is how fast? The order of convergence, the rate of convergence. Does it go like 1 over n, 1 over the square root of n, log n, whatever? Next, and this is my main interest, C. Can you give non-asymptotic estimates? As in Banach-Picard. Can you give me a formula that tells me at the nth iteration what is the error? Not just asymptotic, but finite time error bounds. And finally, does this iteration converge? This is mostly theoretical interest because when you run an algorithm, you never let n to infinity. You stop at some moment. So that's why C, from an algorithmic point of view, C is way more important than D. Although it's nice to know that also your algorithm is not moving around randomly, but it converges to such. So those are the questions for the analysis. I give you the pi-n and I ask you all these questions. The other, perhaps more interesting question is the design issue. Among all these algorithms, which is the best one? How can I decide whether my pi-n is good or not? And hopefully, which is the best optimal pi-n? This is a sort of design of the most efficient algorithm within this class. That's the analysis. So this objective function is pretty weird. So you look at the nth iteration of a generic iteration of this type. It depends on pi, basically, and x0 and the operator t. And now you look at the worst case. What is the worst residual that you could observe if I let the operator t vary along any space, only restricted to being non-expansive? And also I vary the initial point. I look at the worst case. So this is an infinite dimensional, very complicated space of every operator. So it seems intractable.
You're also letting the norm.
Yes, yes. I'm varying the norm, the space, the operator, and exit. And I take the supremum. What is the worst thing that can happen to my algorithm with pi-n?
Why do you say you're varying the norm? Sorry.
Well, there is a norm here. The operator t is defined on a certain space, x norm. I'm looking for this objective function, which is the supremum over all operators t. The operator t comes with its own space. So I let you choose. I want to have a uniform guarantee. Uniform guarantee that works for any operator in any space. It looks intractable, of course, but I will try to convince you that this can be computed explicitly. That will be my first part of this. But before, let me shift to some examples. So here's the first, very simple. Take a rotation in R2. This is a rotation in pi over 4. If you do Picard, well, you just turn around and you never converge. Of course, the only fixed point is 0. It's a linear map. The only fixed point is 0. If you iterate from x0 to t of x0 and then t of x0, you just turn around. It doesn't converge. What happens if you do Halper for 1/2? Sorry, not Halper, Krasnodębski map. Well, instead of making the full step to t of x0, you just stop at the midpoint. And if you iterate this will start spiraling down to the origin. It does converge, like in this case. You can come up with explicit formulas, but that's not the point. The point is that by just introducing this averaging trick, the things suddenly converge, despite the fact that the operator is isometric. It's not contracted, right? So this rotation will converge. How does this compare to Halper? Well, here's the answer. The stupid idea of Halper. So this is again Krasnodębski man, converges by spiraling. And here's Halper. This idea of averaging with respect to the initial point, the anchor point, that's a sort of spiral, but then it turns, and it goes much faster. In fact, I anticipate the results. You can prove that this converges as 1 over square root n. This one converges as 1 over n. But there is an acceleration. Halper tends to work better, and this can be substantiated by theory. Next example. This is not an algorithm. This is just approximation of Poisson distribution by Poisson binomials. But it can be seen as an iteration of Krasnodębski. So take this operator in L1, the right shift, where you just move one place and you insert a 0. This is the operator. You start from 1, 0, 0, 0. Next iterate is 1 minus alpha 1, alpha 1. You just shift, put an average with 1 minus alpha 1 and alpha 1. Next step, x2, you just average this with 1 minus alpha 2 plus this one shifted multiplied by alpha 2, and you get this expression. And if you keep going, what you can see, and you can be convinced pretty easily that The nth iteration will give you just the distribution of a sum of independent variables with parameters alpha I. So if you take alpha constant, this will be the distribution of a binomial. Otherwise, if the alpha i's are different, this is called the Poisson binomial distribution. And these distributions are well studied. There is a lot which is known. In fact, they are unimodal, they go up and down. And the fixed point residual is just the 2 times the maximum height. It's a trivial calculation. And if you look at the continuous semigroup associated to that, so instead of doing the iterations, you look at the continuous t over tx over dt equal minus I minus t, then the solution of this equation is just the Poisson distribution. So you can study, there is a connection between this type of iterations and approximation of distributions. That's a different motivation. Again, this map is not a contraction, it's an isometry, right? Next example drawn from optimization, filtering of images. So suppose I have an original image, which I suppose some regularity, some space, omega is a bounded domain in R2. I have this grayscale image, and I don't observe X bar, which is the true image, but I observe a blur image. So there's a blurring operator B, which is supposed to be known. It's the effect of the atmosphere or something about your camera. Okay, the physics of your camera says you will not capture the true image, but with some blur. And on top of that, you will have some noise. So that's what you observe, Y, and you want to recover X. So here's the original image, here's the blurred image. This is from a spot satellite. And of course, I put here in the infinite dimensional setting, but in practice, these are just pixels image. So the image is at 2 times 256 times square pixels of grayscale between 0 and 1. There are many things that happen down here, the blurring, the filtering, and so on and so forth. But one, which is restoration with total variation constraint, looks like this. Take it here to reference, but there are hundreds of people working on that specific area. So what you do is you try to find the X, which is supposed to be the recovered image, whose image by the blurring operator is close to what you observe. Why? You add some regularization. In this case, it's a norm square, just to avoid excess that are to be a trick. And then you constrain to some prior information that you might have on the image. Here are some examples. For instance, you know that your image is between 0 and 255 levels of gray. That's one constraint. The other is that the total mass is given. The other thing, which is the total variation constraint, is that you want something whose norm of the gradient integrated over the domain is not too large. This is a trick to try to create contrast and detect borders, contours. And here's the algorithm. It's called projection onto convex sets. You define this operator T of X, which is the average of the projection on the individual set. Usually, this projecting onto this intersection is complicated, but perhaps projecting onto each set could be easier, right? So what you do is you take these projections operator, all of them are non-expansive. You take the average, it's still non-expansive. And here's the algorithm that they propose there. Look at line 2. Line 2 looks like a Krasnodębski iteration, except that here there is a sequence Z, a sequence XM, intermediate that is found somehow. And again, this has the flavor of Krasnodębski. Next example, Markov chains. So suppose that I give you a Markov chain which has a finite state space. You have a finite matrix, transition matrix P. If you start from an initial distribution, the evolution of the chain is described by simply this pre-multiplication of P by UN. This is the of the evolution of the law of the chain. And for ergodic chains, I don't enter into details, but ergodic is a sort of contraction property. Yeah? You can show that this iteration, which is just Banach Picard, converges to the unique fixed point, which is the invariant measure. In general, if you don't have ergodicity, what you can prove is convergence in ergodic terms. So the Cesar means along the iteration. So if you look at the laws, you average them over n, and this will converge to an invariant law. And if you look at this is a definition. This is the evolution. It's not an algorithm. This is the way the Markov chain evolves. You look at this object here, the Cesar means. Well, if you work out this, it turns out that this is just hyperiteration. You can look at Markov chains or ergodic convergence of Markov chains as one instance of a hyperiteration, where the operator P this time is non-expansive for a L1 norm. So again, no contraction, there is non-expansivity, the norm might not be Hilbert or maybe not so well behaved. The L1 norm, the previous example was an infinity norm. Well, maybe I will skip this one. Laser random walks in metric spaces can also be seen in some cases as KM. This I should say a few words of this. There's a full area of research in probability theory, which is called stochastic approximation. The origins of that is an algorithm proposed by Robinson Morrow in 1951, where the question was very simple. I have a certain radiation theory whose effectivity depends on the intensity. There's some parameter X, which is the amount of drag that I inject. And the reduction of the tumor depends on what is the amount of radiation I disrupt. So the effectiveness is in fact a random variable. It depends on the patient. But it's a random variable which has a mean, which is increasing with the treatment intensity. The question they ask is, how can I find the right level of treatment intensity so that I achieve exactly a reduction, let's say, of 90% the tumor? That's my objective. Reduce the tumor to 10%. The reduction is 90%. And they said, okay, here's the strategy. Trial and error. Pick a patient, try with 1x1, observe the outcome, and then update. Very intuitive, vague idea. So I take different levels, I try one after the other. If the outcome is bigger than my target role, if I went too far, then I reduce. If I was short, then I increase. And that's this direction. Now this is a cross-process schema. Again. And in fact, it is the starting motivation for the analysis of this Robin-Monroe process, which is a stochastic process of this form, where you have a state variable x, which moves according to a certain field, plus some noise. The noise you assume that is a magnitude difference or adapted to some filtration and so on and so forth. If you look at this type of systems, well, it's tempting to look at this as an approximation of a derivative. If you take expectation, this un plus 1 vanishes. So this can be seen as a randomly perturbed discretization of this ODE. This is called the ODE method in stochastic approximation. And the results are, there are many results, but the typical result is if the differential equations is well behaved, if it has an attractor, then the stochastic iteration, discrete iteration, should also follow this field. That's the message. Okay. Then, of course, there are conditions on the alpha m's. They must be going to 0 because, the two dynamics become close. Well, in this case, this holds. This is a differential equation, and of course it converges to it. It has an attractor, which is the only X star which satisfies rho minus m of X star equals 0, which is the stationary function. But of course, this stochastic approximation fails on one point. It doesn't provide you with finite time guarantees. And here's my favorite example, as promised. So, control Markov chain. You have a Markov chain which looks like this. So you have a finite state space and a finite action space. You can decide on some actions. And the actions will affect both the probability jumps. So this BJIA is the probability to jump from I to J if I apply action A. And as you do that, along this jump, you get a certain reward that also depends on what was the state I, what was the action that you took, and what is the next state that occurs randomly. And your goal is, so it looks like this. You're at the current state IT, you take an action, the probability kernel selects randomly a next state where you will take a new action, and you repeat this forever. And along this process, you get a reward. There are many things that have been done in this area, but I will focus mainly on this, what they call average payoff. So your goal is to determine a stationary policy, which tells you what to do at every state that you will encounter. You will take an action. Well, this map mu tells you what to do at every state. And you want to select that contour in such a way that this expression is as large as possible. What is this expression? You take your stream of rewards, you average them over a period of time, you take the expectation, that's random, so take the expectation, and then you take the limit. So you want to maximize the expected average payoff per period in the long run. There is another strand of problems where you have discount factors. Here you don't have discount factors. Discount factors make a lot of sense when you're talking about money, when you're talking about controlling a physical system. You want the physical system to operate good in the long term. So that's the objective function. Applications, I'm referring to Puterman. There is a whole chapter that advises for a number of fields where this type of problems arise. So I will not spend time on that. It's just to impress you. There's a lot of applications behind. I'm not a specialist in any of these applications. Okay, so what's the connection with non-expansive maps? Well, it's very simple. Under some very generic condition, very weak condition of weak communication, it's an hypothesis for the random process. Well, it turns out that the long-term average payoff that you will get doesn't depend on the initial state. That's natural. You're looking at the long-term behavior. It doesn't matter where you started. We'll forget. When you take the limit of 1 over n, it doesn't matter where you started from. It's not always the case, but it is the case for weakly communicating. So this optimal value doesn't depend on the initial state. And how, and this is Puterman, how can you find an optimal policy? Well, it's enough to solve in Q a fixed point of a certain operator, h of Q. So think of Q as a matrix where the rows are states, the columns are actions, and QIA is a sort of value or score assigned to state I, action A. Well, you take this matrix, Q, from the space, and you transform into this new matrix in the same space. How do you proceed? Well, for every state and A, I will define my new, and try with the new matrix. I will look at the stochastic transition, let's call it size, the new new state generated by the kernel. And I will take expectation of what? Of the payoff for this state, for this stage, sorry, plus the maximum of what you can obtain, assuming that Q was your future value. It's a sort of iteration. Except that you have to subtract from here R bar. R bar is what? Is this optimal value? Which you don't know, of course. You might know, but it's very unlikely that you know you're looking for an optimal policy and the optimal value. But here's the result. If you're able to find a fixed point of this stage of Q, you're done. You just look at every row and take the action that has maximum Q value. This is called Q learning or Q value iterations. Well, it turns out that this function H is non-expansive on the infinity norm. That's pretty easy to prove, but I will not. And it's not so easy to prove that it has a fixed point. In fact, the fixed point is unique, except for modular constants. See, if I add a constant to Q, the constant will filter out. So if I have a fixed point and I add a constant, I have another fixed point. So there is no unique fixed point, but there is existence. And the other interesting thing is that, okay, you say, I don't know R bar. What about if I just take some approximation of R bar, I replace R bar by R hat? Well, it doesn't work. This operator here has a fixed point if and only if you plug here the correct R bar. You change it by epsilon, there's no fixed point, and the iterations will diverge. So we're sort of stuck here. Moreover, so this map H, if I want to implement the iterative procedure, it has two problems. I cannot evaluate it because of two things. The first one is that the optimal value is unknown. And what is Dayan and Abu Dhabi versus they propose a fix for that. They say, okay, let's replace our bar, not by another constant, which we know it will not work, but let us replace our bar by some function which is allowed to evolve with Q. And you only ask for F to be transparent to constant. For instance, you can take F of Q, the average of all the entries of Q, or any linear form of Q. Just do that. Replace the R bar by this. Now I can evaluate this expression here, except that in several situations, you don't have access directly to the probability. And that's the other problem. That's the learning problem, that you want at the same time to learn the distribution. So you have a system which you know is stochastic, it evolves, and you don't know exactly, you don't have an analytic expression or numerical expression for the probability. But suppose that you have access to a sampling device. So what they propose is to say, okay, let's replace the expectation by just the evaluation on a sample. What you do is take samples and iterate this. This is what they propose. And you see again, 1 minus alpha q minus 1 plus alpha n, something which is almost the operator, except that, well, if you add and subtract the expectation, you have a sort of stochastic approximation algorithm. You have the expectation plus a noise. And the noise is depending on these samples. Okay, so I hope I convinced you that there are at least 3 or 4 reasonable applications. So let's go to the analysis of these many iterations. So the first things that you can easily prove is that any many iteration will remain bounded. Remember that I assumed from the start that the operator T has a fixed point. It's not always the case, but in all the examples I gave you, there is a fixed point. So the first thing that you observe is that the distance, take any fixed point, your iterates will not go away from each star. You cannot prove convergence. In fact, the star of there may be many of them, will not guarantee conversion to a fixed point. So it's a unique fixed point. But you can prove that any fixed point is, your sequence is bounded. The Xn is bounded. And in fact, from this, you derive that your orbits T of xn, so your images will be, the distance from x0 will be bounded by 2 times this initial distance. There is a kappa. This kappa is in principle difficult to estimate because it's starting to know. Okay? But again, the results will deal with, will assume that you have some sort of estimate. Alternatively, if you know that your operator has bounded range, for instance, well, you can replace this kappa, which you don't know this star, you just replace by the diameter of your range. Okay. So let's, from now on, I assume that we have a kappa, and I will assume moreover that kappa is equal to 1, which is not restricted. I can always rescale the norm so that this kappa becomes 1. Okay. The second thing, just to get rid of convergence, was my last question. The issue is that once you have that the residuals go to 0, convergence comes for free. Well, not totally for free. You need that the averaging coefficient satisfies sort of monotonicity condition, which in all the examples I gave you, Halpern, Iman, Nearshot, it's always satisfied. So it's almost for free, this condition, and then the real issue is to prove that the residual goes to 0. Once you have that, the iterates will converge to a fixed point. Even if there are many of them, somehow they will choose 1 and will converge to 1. It depends, of course, on your x0, and if you change your x0, you will converge to a different star, but it converges. And okay, this was for finite dimensional. For infinite dimensional, you get weak convergence, but okay, let's keep that. So now the goal is, how do I prove that the residual goes to 0? And I go back to this objective function, and I claim that we can compute that object by using techniques from optimal transform. The idea is quite simple. Remember that we're in a normal space, so we don't have much. Don't have parallelogram, identity, and Hilbert. You only have triangular inequality basic. That's all you have. So here's the approach. Suppose that somehow I'm able to estimate the distance between 2 arbitrary iterates, xn and xn. We will see later how to do that. Well, if I had some estimates of the distance between 2 iterates, and including the first one, x0 minus t of xn, which is kappa, okay, which is bounded by kappa. Well, if I have those, then the residual xn minus t of xn, well, xn was the average of t xi minus 1. The sum of pi n is equal to 1, so I can include t of xn inside. I can do a triangular inequality, and I derive this expression that provides a bound for the residual. As a function of what? Of this di minus 1n, which I should find somehow. So that's the next question. How do we find good estimates? Well, for x0 minus t of xn, which is the first term here, the d minus 1n, you can just take kappa as an estimate. For the other ones, we will develop a recursive form, which provides the new estimates, assuming that you have already computed the previous estimates. And from now on, I assume kappa equal 1. So here's the idea. I have my iterate xn. I'm trying to find d and n, an estimate of the distance between xn and xn. So xm is an average of this trajectory. This is the definition of them. Similarly, xn, the red stuff, is average with respect to their own weights, the weights by n. And they look like this. These are distributions. Let's look at them as measures, discrete measures. And now let's consider a transportation map that sends the blue mass into the red mass, an arbitrary transportation plan. It's just described by z greater or equal to 0 and balance of mass. I'm shipping this blue mass into the red mass. These are poly, right? if I plug this expression for pi m here and this expression for pi jn, I can rewrite this as a double sum. And now let's take triangular inequality. The norm of xn minus xn is less or equal than the norm of this. T is non-expansive, so I will get rid of t. And I get this, xn minus xn is less or equal than the double sum of this particular transport plan times the previous iterates, which I assume that I already computed. I already have bounds, I minus 1, j minus 1. So for every transportation plan, I have a valid bound. If I want the best bound, well, let's minimize this expression. This is a linear function subject to linear constraints. It's a linear program. Let's minimize that. That provides the best optimal bound that I can get by just this naive technique. Well, it turns out that the bounds that you obtain this way are tight, uniformly tight. So despite that you are doing majorization by nodes and so on and so forth, you cannot do better than this. And this is the first result. So here's again the recursion. DMN is the minimizer, is the minimum of the previous. So that's the recursion. It's a double recursion in M and N. And once you have this DMN, you define your residual, estimate Rn. It's just a summary of what I wrote previously. And then what I already proved in the previous slide is trivial proof is that for any T non-expansive, the non-iterate satisfy this bound DMN and the residual. The proof is checked the previous slide, so very easy. What is a bit more tricky is to prove that there exists a non-expansive map where you have equality here and here all along the iterate. So that in fact, this phi n of pi is just the Rn that I computed here. Now, computing Rn is not so easy. You have to compute all the DMNs and so on and so forth. So we'll try to do something. Well, there are some interesting properties of this DMN that I just showed you. So again, here's the recursion. Well, it turns out that this DMN define a metric. It's a very weak metric because it's bounded between 0 and 1. If you fix n and you start at 0, then your distance is 1. Then you start decreasing. And you get to m is 0. I'm moving m now. And then it goes back to 1 asymptotic. It's a bounded metric. Not only that, well, this I said here, DMN decreases when m is getting closer to n and increases afterwards. And moreover, it satisfies this quadrangle inequality, which is a stronger condition than the triangle inequality. So it's the following: if I take I, J, K, L in this configuration, then the sum of the distance without crossing is smaller than the sum of the distance where you have the crossing. This is the quadrangle inequality. If you merge J with K, so if you take J equal K, this is just the triangle inequality. Because the distance from J to K is Z. Okay, so this is an improvement of, it's related to this, how to call that? Never mind. So this has an interesting consequence, is that if I'm trying to compute an optimal transport, I should try to avoid sending flows on crossings, because I just can uncross and decrease the optimal value. So that this implies that your optimal transports have a nested structure, which in fact gives you a greedy algorithm to compute. It's called the inside-out algorithm, which was one of the conjectures in the original paper I mentioned, by Daniel and Brooke. Well, it is true. Proving this took us a long time. There was a thesis by Satik, where the proof was never checked, never published. Contacted Bayona, contacted Brooke. They said, we believe it's true, but we cannot, sure. It's a nested recurrence of 4 levels. So you have case 1, case 2, case 1A, A1, A1. It's very different. So we couldn't understand. I realized that I read against a text business, I could never understand that. It seems correct. Well, we found a way around and proved it like this condition. So with this, for instance, if I take Krasnodębski man, let's say a constant alpha, because I would have the fact that the optimal transport doesn't cross gives you the structure of the optimal transport. You just send across as much as, so you satisfy all this demand directly, and the rest you just send it to it. So it's a very, trivial. You don't have to solve a linear program. That's the solution. And if you do that, for instance, here's what you get. The distance from 6 to 10 as a function of alpha gives you this type of very nice polynomials with integer values. Have you ever seen this? No? Neither do I. And here are the residuals. Again, very nice polynomials with integer values, alternating, power. Well, it took us almost 4 or 5 years to discover what is this object. Now we know exactly what it is. We found the result, we found the answer by reading some papers on lattice paths. You can come up with an explicit formula for this, but I will not show it. It's an ugly formula, but it's explicit. If you do Krasnodębski man, for instance, with 1 over n plus 1, where you decrease the weights, you can again compute explicitly the DMN. Here's the matrix, here are the Rn. You can compute exactly because of this greedy algorithm. We don't have a closed formula so far. We don't know what is this or what is this. What are these fractions that appear? I don't know. Numerically suggest that this Rn behaves like 1 over square root of log m. Is the speed of convergence if you want. How much time do I have? Because I'm usually very slow.
It's 2:33, so 7
minutes. So let me just, I will not go to the applications. Let me just summarize. I want to show you what is the error bound that we can prove for Krasnodębski man. Well, the summary is here. So, okay, I will try to cut short. So the story of Krasnodębski man is very long. It started with Krasnodębski, then Schaeffer, then Edelstein, blah, blah, blah. They were all proving basically that the norm converges to 0 in a strong sense, not weak convergence, but strong convergence. So that's the key to prove all the other results. But the difficult point in all these works was to prove that the residual converges to 0 strongly. And all of these were done with spatial restriction on the space. Hilbert and uniformly convex and different extensions until Ishikawa in 1976 came with a completely different approach where he showed that in fact no restriction on the space. Just any normal space. And that was quite a surprise by that time. Everybody believed that the structure of the norm should play a role. Well, it doesn't. And then shortly after, they started finding guarantees. For instance, Edelstein O'Brien showed that this convergence holds uniformly with respect to the initial point. And then Göbel-Kirch showed that it was uniformly not only with respect to x0, but also to t. Once here I'm considering an operator which operates on a complex set C. And this is the paper I mentioned earlier. This is a very nice paper. I insist to recommend it. Beautiful paper. And they consider a case of Krasnodębski man with alpha constant, and they were able to prove a rate of convergence, 1 over log n. No square root. I think there is a square root here. Maybe not. Maybe log n. Yeah, log n. And they made several conjectures here, and in 1996 they proved one of the conjectures. The conjecture was that, in fact, and this was conjecture in terms of numerics, by numerical experiment, they said, no, it's not log. It should be like square root. And they proved it in 1996. Later, there is a Kohlenbach that proves that, in fact, the uniformity depends on the set C only through its diameter. And the conjecture, it says that the residual should be smaller than rho for some constant rho times this kappa that bounds the orbit divided by square root of sum of alpha 1 minus alpha. That was the conjecture. And they proved it, in fact, for alpha and constant. And they discovered that it would work if you put rho equal 1 over square root of pi. It appears square root of pi. That's a bit unexpected. You're not working, there are no circles here. So why pi should show up? There's no large deviations, no central limit theorems. Why square root of pi? Moreover, this proof here was computer assisted. It's a very intricate. I will try to very briefly show you what are the steps, because in 2014 with Jose Soto and Jose Weisman, we were able to prove the full conversion, the full conjecture for any alpha, and moreover with a human assisted proof, not computer assisted. But still, we were a bit puzzled about this square root of pi, saying, okay, maybe it's just an artifact of the proof. It turns out that not. With Mario Bravo, we proved that, in fact, if you want to have this estimate, the best constant that you can expect is 1 over square root of pi. If you take a smaller constant, I can provide you an example that violates the requirement. So square root of pi is something intrinsic. Why? I still don't have an intuitive reason, or I don't have a good explanation. Why square root of pi? I will show you the analysis where it comes. For affine maps, you can do something better. And okay, if you go back to this, so the conjecture is what? For Krasnodębski man, this Rn has a simpler expression. It's just dn n plus 1 divided by alpha plus 1. It's not the average of all the previous. It turns out that for Krasnodębski man, you have a simple expression of Rn, so that the theorem or the conjecture boils down to proving this inequality. But again, the dn n plus 1 are this optimal transport, difficult to estimate. So what we did, in fact, I'm telling the story in reverse. We started by considering this suboptimal path, and then we discovered that we could do that. So you consider a set of suboptimal paths where basically you send flow across and cost 0, and then the rest you distribute proportionally. Very simple transport, really. Yeah. And then you get an upper bound, because these are suboptimal transport. This DMN are smaller than a CMN. And therefore, the residual can be bounded by Cn plus 1, alpha n plus 1. It turns out that the CMN, which are satisfied, which are characterized by this recursion, now explicit, no optimization, it's just a calculation. This recursion has an interpretation in terms of a Markov chain. This is the Markov chain. It's a persecution, how do you say? It's a run between Coyote and Roadrunner. They start at certain positions, M for the Roadrunner, N for the Coyote, and the Coyote wants to reach the position wants to capture the Roadrunner. To this end, he must jump here a series of hurdles, and he will succeed with probability 1 minus alpha I, and will fail with probability alpha I. Alpha I is being the coefficients of the Krasnodębski man interaction. So you take these Bernoulli variables, which are the failure probabilities. So the Coyote will jump until it falls. What is the probability that he falls at some intermediate point? Well, you get exactly the coefficients that characterize Krasnodębski. If he reaches here, you end. Otherwise, if he falls before reaching the position M, then it's the turn for the Roadrunner to do exactly the same, run away. So They alternate, one advances, the other advances, until one of two things can happen. Either the roadrunner is captured at some stage, or the roadrunner reaches position -1. This is safe. Okay, this is the house of. So the iteration goes like this: you start here, next iterate here, next iterate here, observe. The roadrunner wins. Another run. You start here, you go there, and now, oh, the roadrunner is captured. Now, look at the probability of being absorbed at R. If you look at this absorption and you condition on the first jump, you get this iteration. So it's exactly the thing that you had before. And now everything boils down to calculus of probability. You can, well, you can express that in terms of the CI/RI, and then by some transformation, you reduce to a random walk. I will jump here. We start looking at this. There is a way to reduce this probability to a certain gambler's ruin, which is known. So basically, I want to only to focus on this thing. You get an explicit expression of here with equality. It's just the expectation of some known function, which is known from probability, from the gambler's ruin. And the expectation is with respect to M. M is what is the number of moves. So, when you interpret this is a lazy random walks, where at every position you flip a coin. With some probability you will move, with some probability you will stay still. And once you decide to move, you will go left or right with probability 1/2. That's the lazy random walk. You transform into this expression. So the conjecture is this one. You look at this expression, so you multiply by this, you get a nice function R of P. This function R of P is very nice. It has an optimal where the PI can take only two values. Either 1/2 or some intermediate value. And then you analyze this in the case where all are equal. You get an expression in terms of hypergeometric function, which is smaller than 1. Good. If there is some PI which is 1/2, you do otherwise, but again, you prove that it's smaller than 1. Finally, and this is my last slide. So putting together all of this, you obtain that the expectation of this f of m is smaller than 1 over square root of pi. The square root of pi appears. Why? It's because this hypergeometric function has satisfied certain inequality for these special functions. And therefore, translated into the error bound, it tells you that xn minus t of xn is smaller than kappa divided by square root of pi tau n, where tau n is the sum of the. Can I have 1 minute more?
Yeah.
1 minute. You can extend to iterations where you have errors. And errors can be of two forms, either controlled. If you control the error, you have this estimate, but sometimes the error are stochastic. So you can extend your error estimate to the case where you have controlled errors. And you can also deal with the case where you have stochastics. Get something else, jump here. And if you go back to Q-learning, if you apply all of this finally to the Q-learning, you obtain that the error bound of this Abunadi-Versekas-Borka was unknown in expectation as a bound which is kappa A divided by square root of tau. And it's an explicit constant kappa A. So to summarize, I'm not telling you anything about hyper. That's much simpler than what I just showed the hardest part, which was the longest part, which combines. I think it's more interesting because it combines techniques for optimal transport, then Markov chains, then special functions, combinatorics. So it's a mixture of tools that you pick here and there to get this very simple estimate of 1 over square root of pi. very proud about that. It wasn't our conjecture, it was again because of Diana Brook. And then we have been working later in the extension to the case of error iterations with errors and stochastic iterations. And the applications for Markov retrievers. We keep working on that. I've said on many of this. So, sorry for going over time. Thank you for your.
Thank you. Guys, questions, please. Only one.
So in your example, you heard that Halpern converges much faster.
Yes.
So is this a systematic behavior?
Yes.
You always try to use Halpern.
Yes.
Okay.
Yes.
And sorry, does that translate in some sort of more or higher or smaller robustness to noise? Or
That's a very interesting question. It's that indeed for deterministic iterations, Halpern works much better. But the problem with Halpern, the principle of Halpern is what? You have a non-expansive map and you average between x0, which is a constant function, and beta n, your operator t. So somehow you're gaining contractility. Because x0 is, so the principle is very different. You're trying to induce some contractility, but you have to relax. Your beta n must go to 1. Otherwise, you will be computing the fixed point of something else that you don't care about. So the coefficient in Halpern is forced to go to 1. And the typical choice is n over n plus 2, or n over n plus 1, or the one that we discovered, which is the optimal Halpern you can characterize also, which is the best beta n, which is built recursive. But the problem is when you have noise. When you have noise, is your operator beta n. Let me go here. The case with noise. Okay. This is your iteration. Suppose that I put here x0 and beta n. Your noise here is scaled by beta n, which goes to 1, so it will never vanish, will not disappear. In contrast with that, Krasnodębski man, when you take alpha n going to 0, the noise gets multiplied by alpha n. So there is an implicit variance reduction that operates when you do Krasnodębski man, which will not occur in Halpern. That doesn't mean that you cannot work with Halpern, but you have to provide an extra layer of variance reduction just to kill the noise. Okay? So my take on this is that Halpern works well when you can sample, so you can make the variance reduction. If you cannot do that, then Krasnodębski man doesn't need variance reduction. It has a built-in variance reduction. But this is not a theory. This is just a guess.
I'm curious about the how did that this result apply in the case of rounding? The non-expansive part means less or equal than 1, but what about if we're 1.05 or something?
Yeah, I mean, the rounding errors, they are treated, there are two questions, to answer to your question. Here, I'm assuming that the error here is controlled. Namely, I cannot evaluate the operator T, but I have a subroutine that computes T up to some precision, but I'm able to control how much precision I require. And in fact, the convergence requires some assumptions on the control you have. Along the iteration, you have to improve your precision if you have any hope to be converged. Now, there is a very nice paper by the German guy. What's his name? Where he addressed specifically the issue of rounding them. So he performed several examples on operators that, in theory, you can compute. But when you run on the computer, you have, because of rounding error, you have this precision. And it was very nice what he discovered. What he did is that if you run your algorithm, you will see the noise moving here and there. But then he zoomed in into the noise. So he removed the mean, the average, and he just focused on the noise. And he discovered that there is a very clear pattern. So these rounding errors are not random. They have a very nice profile, probabilistic profile that resembles a certain distribution. I don't know if they figured out which distribution is that, but when you run from far it seems random. When you zoom in, you see that it's not noise. It has a very specific pattern. That's all I can tell. I don't know if this.
Yes, that's
your assumption.
but okay, I'm thinking on station B.
Okay.
The version of the past. But with so you're inverting something. Okay. But I was curious about exactly what happened there. If you have any estimates, what you're going to.
Yeah, well, it depends on how well posed is your solver. If you have a well posed solver, then you can control the error. That's fine. But you have to increase your precision. So that means that you should refine your mesh as you advance. Like I don't know. I'm not a specialist in PDs. Unless I'm not in numbers.
Yeah, I'll just show my ignorance about the decision processes. I think there is some result. So in order to apply this machinery there, you're assuming that your optimal policy, or you're assuming that your policy is a function of the current state, right? But there is some result. Is that a restriction? Is that an assumption? No, there is some result that says that optimal policies have to be okay.
Don't have to be, but what it tells you that there is a result, well-known result. It's not completely general, but for many, for the discounted case, and for the average case with finite space and finite action space, if I'm not wrong, they also assume weak communication. But it's a big class. Then there's a result that says you could think of very sophisticated policies, which could depend on the full history of what you have observed. If I try this several times, then next time I will try something else. So you could do very sophisticated adaptive policies and randomized policies. You're not forced to take a single decision. You could randomize. And the result says that whatever you can reach with this sophisticated history-dependent randomized, you can get exactly the same with a deterministic Markovian policy.
So it's not very
It's not a research. That doesn't mean that it doesn't pay off to do some adaptivity. In fact, in the learning literature, there is a lot of adaptivity that is explored. Because they're trying to estimate several things at the same time, evolution. So there are these X3 techniques that basically what you do is you sample, you explore, and at some point you exploit. And exploiting, that means concentrating on actions that give you good rewards. But since you don't know which actions give you good reward, you have to spend some time exploring. And then little by little, try to focus on the most promising actions. And these are state-dependent dynamics.
But theoretically, there is some result that says that under certain conditions, I can optimize the reward among all policies with memory just by focusing on the canons.
Absolutely, yeah, absolutely. This you can find in Utterman's.
Okay.
Saturn Barto, and now these are well-known results.
Right, that's why
And it's kind of intuitive. First, why don't you have interest to randomize? Because you're looking at the expected value. The expected value is an average. Well, if you average between three optimal actions, or you take one optimal action, it's the same average. So randomizing is a linear function, you're optimizing over a simplex. And the simplex, well, you have the optimum at one extreme point. So that's deterministic. On one. Why does it pay to take account of the history? Because of loss of memory. Because you're only caring about the long run
So if you
evaluation of your payoffs.
I see. You're interested in the finite horizon, then
That's a different.
I see.
No, that's much more difficult. Okay. I mean, not more difficult. Formally, it's easier, but computation is more difficult because you don't have a fixed point. You have to really start typical thing like dynamic programming. You start from the end and then you backtrack. You start from the final horizon, you have the final payoff, and then you have to solve the backward recursion. But that's a very different world.
Yes,
I mean, also related to that, so you have the result of the Markov decision process where you have a little perturbation of R bar, then you don't have fixed point.
No.
Yeah, but then you show results that if you estimate R bar in that, like converging at a certain rate, then you do converge to the fixed point. Are those results and those techniques in the same spirit as these other more general results for the iteration, or they're completely different?
Not sure to understand your question. So
Because
you replace the R bar by a function of Q.
Yeah.
And you expect that this will automatically adjust and eventually convert to the R bar.
Yeah.
You prove it thoroughly. Right. And it does converge to R bar. And the point is the following, is that if you look, when we go back to the model, to the fixed point equation. This operator is invariant or like addition of constants, not invariant. So that is, anyway, if you take Q and you add a constant, the constant comes out. Okay, so that in fact, looking at this map, you can quotient, you can pass to the quotient space, where you identify all matrices Q that are equal, except for a constant, they're equivalent. If you do that, then in fact, you're iterating in this quotient space, it doesn't matter what R bar is. Okay? But of course, you don't want to iterate in that space because the description of equivalent classes is a mess. So you want to keep your iteration in your nice space RSA. And then what you do is just move this R bar by some function, f of q that equals. Now, there's a caveat here, is that when I introduce this f of q here, the operator is no longer non-expansive. You lose non-expansivity. And there you have to be careful because what you do, you run the theoretical iteration with R bar, and you run the true iteration with f of qn. And you show that you can do a coupling of those two, and you show that their difference is just about. You get around this difficulty basically by passing to the quotient space without the need of going to the quotient space. That's it.
Hey, let's give a.
Okay,
Yeah.
thank you very much for your attention.